Good afternoon, neighbors. So my last video was about one of the features, one of the challenges with measurements that most people don't even need to understand. The bulk of the measurements we're doing nowadays are based upon us seeing, right? We see electrons moving. This is the basis of electronics. That's the name for it, right? It has to do with how electrons move around. Those electrons move based upon the molecules that they're interacting with. Some of the electrons get bound to those elements, those atoms, those isotopes. It's very hard to get them to leave the orbits that they're in. But there's outer orbits available that can take other electrons or pass them along easily. Or depending upon the ionization state, might just capture the electron and absorb it. Capacitors use these functions. So this electron thing is huge, simply because of what I'm recording this video on. Electrons, what are they? They have a mass, they zip around, they can kill you, they can burn you. They can cause issues on a spectrum, a broad range of things. The electrons themselves moving about. We know this because you can get an electrical shock, right? It's not hard to take a little AA or AAA battery and learn how you could kill yourself with that device. A couple other things. So these are electrons. These are part of life. This electron binding, how these electrons of atoms build molecules, how those molecules interact with other things around them, interact with light, visual that we see. Physical, maybe. Rough surface versus a smooth surface, you can feel those things, but our eyes are capturing most of what we know about electron movement. So what gets electrons to move? Energy. These are these energy equations that you hear about, you learn about in physics, you learn about when you get into electronics. I happen to learn more in depth about how we use these electrons, the ability of things to move, change the properties of electron movement to measure gases very precisely in gas chromatographs. Using the heat, a different molecule will extract from a little coil of wire. By counting the electrons that go by that are affected by this action. Very precise electronics, very, very precise electronics. Generations in the making, and it's only gotten better since that was my career, part of it, the building blocks of a career of electronics. So this electron idea in metrology is the physics, the science, the engineering of measurements themselves, what they are, how they work, and what they mean. And therein lies the rub. What do the measurements mean? So we're measuring everything with electrons. I was taught a word commonly used was quantum measurements, because these were indirect measurements. So we're seeing electrons. You're telling me you've got a carbon atom over there, an electron somewhere in between there and a readout has deciphered this. It's a precise understanding of how these things work. It's amazing. So this was institutional learning that I got this from. institutions are important artifacts in our societies. Understanding their roles in places, hard to measure sometimes. So we do these precise measurements. Often they are indirect measurements, but the novice, even the average user, doesn't perceive the depth of understanding of how precise those measurements are or why they are so precise. When you get out into 9 digits, 12 digits of resolution, 12 decimal places, either side of the decimal place, you're talking some pretty sophisticated, well-modeled, well-understood measurements. And I mentioned, what do they mean? This goes back to a question you can have why you see an article about one lab making a claim or a statement about pollution issues, and another lab will say, no, this is not an issue. But it wasn't the lab, it wasn't the exact measurements that issued that, it was the interpretation and the understanding of what the impact of that measurement means, the risks involved with the measurement. I've probably got a dozen or more videos on risks, just quick talks. These are things that to understand within our institutions, like the EPA, there are guidelines, rules, boundaries, things, limits they have to work with, and understanding, a common understanding of how things work. And it's not unfortunate. The only way to learn how things work is to go learn how things work. I have a very good ability to create a tunnel vision about things I'm interested in. It helps sustain a career. But this notion of electron movements, that's what surrounded this career and how we measure them. So, when you get into measurements, there's 2 types of measurements. Broad category, destructive and non-destructive. And it's just, do you have to destroy something, cut it apart, break it apart, take a sample of it to put it into an instrument to measure? That is a type of destructive measurement, when you have to go remove a sample from something that was in situ, in site, in a specific location, and take it somewhere and send it somewhere to get analyzed. There's rules about the material, the container you want to put the sample in, what type of materials that should be so as not to contaminate. And to understand that, you get into this notion of parts per billion resolution of instruments. If I take a sample and breathe on it, I could potentially corrupt that sample. So you do things to avoid that. There are rules and procedures for taking samples for very specific things. And what's the further challenge, destructive or non-destructive? Non-destructive is, say, a lot of optical imaging, where you can just take light and bounce light off of a subject and do some analysis from the light returned to you. Your eyes do that. You look at something and you say, oh my gosh, that's a painting, isn't it beautiful? That's imaging, that's artificial intelligence in your own mind. That's organic intelligence, that's what humans have. This conversation's about measurements. This is something the EPA relies heavily on in order to make decisions. The EPA relies on numbers to open an investigation to get further numbers. They are like any other judicial organization, some type of law enforcement thing, rules enforcement, right? So somebody has to interpret those measurements. has to build a plausible story about the source and the effects of what they mean. Air pollution monitoring. There are two things you want to know about air pollution. First one is, or is it the second one? What is it in the air? Is there something we realistically can do about it? Should we do something about it? Is it systemic? Is it constantly occurring? Is it localized? Is there a point source, or is it something else? So these things, these ways of talking about how you do things is important. In the measurement sciences, there is a chain of custody effect for a sample. How you take the sample is important. Where you send it to for testing is important. If you can afford the testing, that's a big if. What type of testing do you ask? How much do you know about testing? At this point, it's all destructive, right? You've taken the water out of its normal place and you're sending it someplace else. So it begins with a note about where the water was sampled from, what time of day, if it's weather conditions, if it's outdoor water, not so important if it's house water, other than it could be hot water in your pipes because the ground's gotten so warm and now it better breeds bacteria because it's warmer. Measurements. So what do you ask to be measured? The measurements I'm familiar with: gas chromatography, optical emission spectroscopy have specific rules about capturing the samples, analyzing the samples, dissecting them. If an instrument in a process stream is only looking for one element, you know that there's 9, not elements, compounds. You know that there's 9 compounds in that stream, and possibly more because the stream is not ultra high purity, it's just normal common, so it's 97% something and 3% something else. So this is what analysis do you do to find this out? Gas chromatography is a lesson in its own. I understand very well the analog properties of the devices, the principles within the devices, how they operate, but it would take me a lot to specify in a gas chromatograph what type of columns to use to separate the gases for this measurement thingy I talked about a minute ago. This is what happens. This gets complicated very quickly. And if you ask the question, you go down into what some people call rabbit holes. But if it is legitimate knowledge about a subject, then it's not a rabbit hole. It's really learning, something we do for all of our lives, I would hope. Try it. It's frustrating. So, this is where we get clobbered in these conversations about life, about pollution, specifically, every type of pollution. There's specific questions you have to ask. And when you go to get these analyses done, you might have to send a single sample to 7 different labs in order to get a complete assay, ASSAY, because there's 2 levels of this analysis. What compounds are there in these materials? Identifying compounds takes discrete, unique types of analysis, maybe totally different instruments and processes. There's sample preparations, separations, digestions. If you go into optical emission spectroscopy, there's basically, now there's more than, there was basically two types of samples, arc or spark, like a welding electrode. A welder, that is an arc, or spark. Lots of different configurations for how you can arc or spark weld, but that's basically what that type of sample is. You use an electric arc, electricity again, eh? You use an electric arc on a sample to ionize the materials, destruct all the materials, and you look at the light emissions from that arc weld, and you can find the specific elements, isotopes, within that arc stream. You can get more sophisticated than looking at just the light and pull the gas off of those streams and analyze the gas using some type of mass spectroscopy. I submitted a sample to an Oregon University lab, and I did not do my homework, could not do my homework on sample preparation to get it to this lab properly. And that was a TOF SIM analyzer, one of the most sophisticated. This university uses it for analyzing materials for semiconductors and electronics components, mostly. But they will take other samples, but you have to know what you're doing walking that door with a sample. And I knew what I was doing, but I was hoping for some help. And I wasn't effective in getting that, and it would have taken money. So, but that is destructive testing for elements and isotopes themselves, and ions and a few other things that happen when you do these to materials. There's been additional sampling techniques created with the advent of laser technology, so you can use laser ablation to burn the surface of material and analyze the light reflected off of that. There's a little handheld device you can get to do that now if you've got a few bucks. Amazing how small these things got. The one I worked on was a baby grand piano in here, so took forklifts to carry it around. Anyway, this is the world of measurements. This is a very discrete world. The doctors, chemists, and scientists that I worked with on these analyzers when I went into multitudes of facilities, engineers, foundries, nuclear plants, chemical plants, using optical emission spectroscopy for very specific elemental analysis questions, using gas chromatographs designed specifically for a known set of input gases, and just looking for the ratios, the amount of those gases in the stream, to further set up the process downstream, change valve flows, change whatever you need to do. This is how life works. So, how do we make institutions work? You cannot stick the word woke into any of this. It doesn't help. So, there's a too long one, but here's what it is. Thank you.